Chapter 7 is all about the base and the acid. So today we're going to start out with section 7.1 and 7-2, which is discussing the classification of acids and bases. So to begin with, your textbook really describes them as either a sour or a bitter, or maybe it's turning litmus paper red, or maybe it turns litmus paper blue. And these are all just descriptors to help you figure out if you have something in your house. Can you figure out if it's an acid, a base, or a neutral compound? And so I think the most helpful of that is the thing tasting sour or tasting bitter. That might sound crazy to you because typically if you're in a chemistry lab, I do not want you to go around tasting the chemicals. That's not the way it works. But these are instead in here in case you have something like maybe these gummy worms that you see here below. Those taste sour. So whenever you taste something that is sour, know that that's an acidic compound that you're eating. Whereas if something tastes bitter, that's going to be a more basic compound. And then you're looking over here at the soap. Anything that feels slippery is going to be more basic. And so those are your soaps, that kind of thing. And so if you feel it and you feel like it's slimy or slippery on your hand, it's because it's reacting with your skin oils and that's producing the hydroxide. The hydroxide is producing the slippery substances that you feel with the soap. And then also something, just an extra interesting tidbit to you, acids are really important in chemistry. In fact, it's the number one chemical that is produced in the United States is in fact sulfuric acid, which is an acid. And so these are really important compounds. They're used so much in every single part of our day. And so it's good just to know how are they classified. If you go look in your cabinets or in your cleaning supplies, which are acids, which are bases, etc. Alright, then it also talked about this turning of the litmus paper. Now in your lab kit, I think you have something that's more similar to what you see on the right hand side of the screen, where you stick a test strip into it and it turns a magical color, and that magical color tells you the pH of it. Later on in this titration, you're going to actually use a pH electrode. If you're also in the lab component, you're going to use a pH electrode that's going to tell you a digital value for pH. But these test strips, they're used all the time for hot tubs, pools, that kind of thing. So knowing that all it is some dye that's pH sensitive, and that dye changes colors when exposed to an acid or a base, and that is how you're able to figure out what the pH is. It's kind of important to know, but for the most part, this is chemistry that lots of people that have never used chemistry before can figure out. Alright, so now let's talk a little bit about classifying acids. When you classify an acid, there are three main definitions. There's Arrhenius, Bronsted-Lowry, and then Lewis. Your textbook doesn't talk about Lewis, but I wanted you to know that there is a third definition out there. So if you ever hear somebody talking about a Lewis acid or a Lewis base, there is such a thing, but we don't really get too far into it. It's a little bit more complex and harder to identify, so we're just sticking with the first two, that of Arrhenius and Bronsted-Lowry. Now, your textbook made it sound like they were a little bit different, but yeah, okay, they're a little different in just how the definition is laid out, but to be honest, I don't really see a difference. They both end up either donating hydrogen, or when you throw them into water, a hydrogen is released. So in the end, the same goal is reached. You have hydrogens floating around. So I'm going to call that an acid, and that can either be Arrhenius or Bronsted-Lowry, but either way, it's the same thing. So if we look at all of these strong acids that are listed here below, they all have a proton. It's pretty easy to see that those are all acids. So if you have something that is a proton, it has an H in it, it's going to look a lot like an acid. Now there are some things to notice because not everything that has an H in it is an acid, but notice with all of these, the hydrogen is listed first. That's most common of these binary or these compounds that have one hydrogen with one other atom, or a hydrogen with a polyatomic atom. So everything on the left hand side, those are binary acids, so hydrochloric, hydrobromic, hydroiodic. Everything on the right side of this table, nitric, perchloric, sulfuric, those have a polyatomic ion, and then that is combined with a hydrogen, and so those are listed with the hydrogen first. But then you also have things like this, which is acetic acid. Acetic acid always looks strange to students, and that's because you have CH3, which is covalently bound, so that's CH3COOH. The CH3 is very covalent, so those hydrogens are not popping off because carbon bound to hydrogen, that's super strong, not going to happen. Carbon's not going to release the hydrogens, okay? It's just not going to happen because carbon to hydrogen, that's a very stable bond. It's not letting go. But on the other end, that COOH, that's called a carboxylic acid. Anytime you see a COOH group, know that that hydrogen can pop off and become an acid, and that is what happens here. And so when we're looking at these things, you're looking for either the hydrogen at the front or you're looking for that carboxylic acid. And really, for your sake of your textbook in this class, there's really not any other thing you need to look for. See a proton at the front, see a proton at the back, you're good. But that proton at the back better be attached to a carboxylic acid. Okay? But you just said the proton at the back, look for it. Well, this is sodium hydroxide. Sodium hydroxide is not an acid, but yet the proton's at the back. Okay? No. Hydroxide. Hydroxide is different from protons, so that's what you need to be looking for. If that H at the end is not attached to carboxylic acid, then no, it's probably not an acid. It might look like sodium hydroxide or one of the other hydroxides. All right? So whenever you're looking for these, this is literally what's happening. You have like hydrochloric acid reacting with water. Hydrochloric is your acid it's your donor, so therefore it's the acid, whereas water might have accepted that proton, therefore it is the base. So in this situation, water is the base because it's accepting the proton. Hydrochloric is an acid because it's donating the hydrogen. Alright, so question then. How do we know that these are or aren't acids? Because I already gave you those first couple caveats. What's literally happening? So in this case, you got your hydrogen at the beginning, and it is attached to sulfate. And so this is a polyatomic ion attached to a hydrogen. And so when this falls apart, it's going to break apart the two ionic parts. So the hydrogen ion and the sulfate, they're going to break apart from each other, thus releasing hydrogen in the solution. So this would be an acid. Same thing goes for here. You got hydrogen attached to a polyatomic, that of nitrate, and then when you throw it into water, they're going to break apart. And so I'm going to know that these are acids because I've looked at polyatomics prior to this. And if you recall back, I think that was Unit 1, just kind of remember those polyatomic ions. So if you see them and you see a hydrogen at the front, they're going to break apart well. But if you have things like this, NH3, hydrogen's not at the front, hydrogen's at the end. Hydrogen is also not in carboxylic acid. Therefore, you're like, what is this? Well, something to note. You need there to be an ionic bond in order for the hydrogen ion to pop off. So before you had a H with a polyatomic. Polyatomic is a charged particle. That of negative, the protons are positive. In this case, your nitrogen is a nonmetal. Your hydrogen is a nonmetal. Two nonmetals bound together means it's a covalent bond. Whenever you have a covalent bond, it by definition is not an acid ever. Same thing here. Carbon, nonmetal. Hydrogen, nonmetal. Therefore, covalent bond, not acidic. And so that's what you're looking for. Proton at the front, proton at the end. If it's a carboxylic acid, if it's in a covalent bond, it is not an acidic proton. It cannot pop off. Alright, so now let's look at bases. Just like I mentioned before, there is such a thing as a Lewis base, but for the sake of this textbook, we are going to ignore it. Alright, so that leaves us with Arrhenius or Bronsted-Lowry. So when we're looking at something such as sodium hydroxide, you have sodium bound to a hydroxide molecule. When you throw it into water, you release sodium ions, which are the same sodiums from sodium chloride, which is your table salt, and hydroxide. And so hydroxide is that basic element. So Arrhenius said anything that donates a hydroxide is going to be a base. Bronsted-Lowry wanted to go a little bit further and said, all right, I take you, Arrhenius. I'm going to encompass you. I'm going to say, yes, everything that's a hydroxide is a base, but you can still be basic without having hydroxides. And so he went on and performed a whole bunch of really cool experiments to prove this notion. And so in doing so, let's look at table 7.2. You'll notice everything pretty much has a hydroxide. Anytime you see that OH group, just check it off and be like, base, that was easy. But then you have something like ammonia. Ammonia down here is a little annoying little compound, right? So it doesn't have a hydroxide. You can't tell just by looking at it really quickly that, oh, I know for a fact that that is a base. Instead, you have to do a reaction in order to tell. So let's try and react it with a proton. Because we knew from the prior slide that with NH3, you can't strip off one of those hydrogens because nitrogen is a nonmetal, hydrogen's a nonmetal. So we know we can't strip a hydrogen, so it's not an acid. So let's throw an acid to it and see what we produce. And it will, in fact, accept it. So since it will accept a proton, we're going to classify it as a base. But how can it then also be classified as Arrhenius? It doesn't work that way. Everything that is Arrhenius, so if you're in the center of the circle, you're also considered a Bronsted-Lowry base. But things that are not Arrhenius, but only Bronsted-Lowry, they are things such as ammonia that could produce hydroxide if reacted with water. And that's what you see in this reaction here. So ammonia, is it Arrhenius? Does it have hydroxide built into its chemical structure? No. Therefore, it's not an Arrhenius base. Can it accept protons and form a basic compound? Absolutely. And so that's why it is considered a base, because protons, it will react with water, thus forming hydroxides in solution, thus making it the solution more basic. So kind of to recap that, Arrhenius are anything that you look at the chemical formula and you notice, hey, it's got a hydroxide. Bronsted-Lowry are those that will react with protons to produce something that is basic. And so that of ammonia is a great example. Alright, so this is another just pictorial reaction of ammonia reacting with water. And you'll notice that in this case, water is your proton donor, making it the acid, whereas ammonia is your proton acceptor, therefore classifying it as the base. Alright, so amphoteric, that's a fun definition in your textbook. It is any substance that can behave as an acid or a base. And I hope you noticed in the previous slides that if water reacts with hydrochloric acid, it's going to accept that proton from hydrogen, from hydrochloric acid. When it does that, it becomes H3O+, which means it was the proton acceptor, and therefore it was a base. But if you react it with ammonia, it's going to take that acid and donate it to the ammonia, making it be ammonium. Therefore, in this situation, it's a proton donor. Therefore, it's the acid. So sometimes water likes to be an acid, sometimes it likes to be a base, so it gets a fancy word called amphoteric. Or another way of saying that is if water reacts with itself, it can act both as an acid and a base, and it can self-ionize, thus producing that H3O+ and the hydroxide. And so these are just two little definitions that are tossed in here as well, just kind of help you remind you that sometimes you've got your acids and your bases, and they can play both parts of the field. Alright, now, neutralization reactions. A neutralization reaction is what occurs when an acid reacts with a base, producing a salt and water. And so these salts are the same salts that we've looked at before, where a salt is an ionically bound compound. You've got a metal plus a nonmetal. So in the situations down here, you've got hydrochloric acid reacting with sodium hydroxide to produce sodium chloride and water. Sodium is a metal, chlorine is a nonmetal. You've got a metal plus a nonmetal, therefore it's classified as a salt, an ionic bond. And the second equation, you got potassium, metal, chlorine, nonmetal, reacting, ionic bond, it's a salt. Okay? And so that's just the reaction is what is always called, if it's a neutralization reaction, you always have acid plus base is a salt plus a water. And so here's just a couple more examples for you where you've got the salt being produced by the reaction between an acid and a base. Okay, so with that, go ahead and go read section 7.3 and 7.4.